Saxon Algebra 2. Welcome to the last week of classes. The last week of classes get a little weird in Algebra 2 because I combine and skip around a little bit in the lessons. 117 is like the tiniest little bit of fluff of a lesson, but it combines really naturally with 119. You'll see in a minute. It's like a non-lesson. So we're going to combine these into one lesson. This is kind of my revamped week 31. We're going to do 117 and 119 together. Then we're going to go pick up 118. Then we're going to do 120 and 121. So this will be the pattern that we're doing for the last week of lessons. What about all the other lessons in this book? It goes up through 127. I'll tell you what's in here. John is trying to play catch up and give us some lessons on geometric construction, which means using a protractor and a compass to draw things. And he's trying to catch up on some proof lessons, which means taking geometric shapes and using what we know to prove that certain parts match. This is not a good time of a year for John to take us down two brand new and very mind-bendy pathways. That makes no sense. I have strong feelings about construction problems because the tools that are available today, compasses in particular, are shoddy and extremely difficult to do precision work with. And I don't want to set up my students with the frustration of trying to do precise, exact drawings with cheap instruments that slip and fall apart. So that's my main reasoning. I'm not doing those. You're not going to need them. I mean, if you ever run into one problem on those on a standardized test, call me and let me know, and I'll apologize to you for not preparing you. Proofs we are going to do. We're going to do them next year, and John lays them out in a really good, understandable way in the green book. He dives in too fast and too deep in this book, so I don't want to confuse you at the end of the year with a bunch of poorly designed lessons. Let's wait and handle those next year. So that's why I make the changes that I do. Here is what I want to show you about set builder notation. I'm just going to show it to you in the example, and then I'll go back and explain what you need to know. This is from 117. There's just one example in 117. It says this. Write this down, and you'll be like, what? And then I'll explain how easy it is. Pretend that's all in one line. Okay, I'll let you finish copying it, and then I'll explain what it means. What this means is that x and y are elements of the real numbers such that, I'm just writing in some of what I've already said. X and y are elements of the real numbers such that y is greater than x plus 2 and y is less than x. What on earth is this crazy way of writing the problems? I know, it's called set builder notation. All it is just a slightly different language for presenting the information. But look. If I do a little dotty, 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 dash to separate the two. Can you see that this problem, which looks quite familiar and very doable, I hope, this is exactly the same as this. Y is greater than x plus 2. Y is less than minus x. Yes, that's a system, so and is an appropriate word. Domain equals the reals. That's what this is trying to say, is domain equals the reals. So this is a very familiar problem. It's exactly the same as what we've been doing. There's nothing different about the math. All that's different is the notation. This is just a different way of setting it up. In order to know this, we need to know how we use these letters to represent the different groups of numbers. And they're fun to draw because they all have this like double line. These are what we call the natural or counting numbers. It's kind of like an N with a double line on it. Just a plain W are the whole numbers, right where we include 0. This is the one that we'll use a lot of the time. This Z is the integers, which is kind of weird, but I'm glad because it's really fun to draw that. And then John goes on with the list. These are the ones we're going to really use all the time because those are the domains that we typically use. If you look on page 117, there are more of them. I'll show you, but we don't need to write them all down. Here's a Q with a line through it for rational numbers, P for irrationals. We did the one for the reals. Complex numbers, which you know is where there's a real and an imaginary part. That's a C with a slash through it. Through next year, I don't know that you're ever going to use any of these except for integers and real numbers. So the Z and the R, right, are the ones that we're going to use. Okay, so the way we do this problem is just the way we do this problem. I guess I have to rip it out. I have to flip, rather. All right, so the way we'll do this is to say we want to graph the real numbers. Okay, so that's arrows rather than dots. Oh, it's, I see I have an X and a Y, so that tells me we're not on just a number line. We're on the whole Cartesian bad boy. And we want to graph this and this. So it's Y is greater than X plus 2, and it's Y is less than minus X. And we're using the real numbers, so I'll just copy that. So let's see, this I'm going to graph as a line, but I'm going to use just the dashes, not the solid line. There's my slope. So here's my positive 2 y-intercept, and then I'll go up 1 and over 1 for the second point. This is dashy. Okay, y is greater than, so that tells me I'm going to be going this way. Okay, now I graph the other line. Because I can, I've got other colors right here. I'm just going to use them. Okay, so this is going to be in the green. So this I can add the 0 because that gives me a y-intercept. My slope is negative 1 over 1, so I go down 1 and over 1. This is also dashy. Y is less than, so that tells me I want to go to this side. And then here is my overlappy area, right? This is my solution where the two overlap. And as you can see, John agrees with us, right? Okay, so that's all there is to lesson 117. You're now cleared to do those problems. When we get to 119, we're skipping 118. All we're doing is absolute value inequalities using this new set builder notation. So there are how many here? And there's 4 of them. They're fast though. Graph. X is an element of the real numbers such that the absolute value of x minus 2 is less than 4. Okay, we don't have to rewrite this in the style we're used to. We can work with it from this. We know absolute value is going to break into 2 non-absolute value expressions. We take x minus 2 is less than 4, and we take x minus 2 is greater than, we reverse it, and then we take the negative. That's how we find the 2 different options when we're breaking down an absolute value. We do the algebra, we'll add 2 to both sides. X is less than 6, and then we'll add 2 over here. X is greater than minus 2. So we're looking for a solution that will respect both of these, and we're looking for real numbers. That's great, that means arrows. So here's my 6 with an open circle because I don't have an equal sign. Here's my minus 2 with an open circle, and we're looking for the space where they meet in the middle. Yay, that's the right answer. Okay, so again, let me point out, the only thing that's different is how we're writing down the problem. X is an element of, that Z is just so cool. I love drawing it. It's the integers, so not the reals, these are the dots. I still like to write arrows and dots by my domain. Absolute value of x plus 2 is less than or equal to 3. Okay, so we remind ourselves we're just going to graph this, and this tells us the domain. It's absolute value, so we got to break it down. X plus 2 is less than or equal to 3. We do the first one exactly the same, just take those off. And then we take them off a second time, but we reverse the inequality, and we reverse the sign on the other side. Okay, I'm going to subtract 2. X is less than or equal to 1. And x is greater than or equal to minus 5. All right, so we're looking for numbers between less than or equal to 1. So I'm going to go minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2. Wow, that worked out really well. The reason I did it like that, I'll show you just a second. Let me write them in. I know that I'm going to be starting at 1 and going down, and I'm going to be starting at minus 5 and going up. So I made my number line just big enough so that you can see 1 point on either side that I didn't choose. And that way you can see the solution more clearly. And how did I do? That's right. If you're doing these problems and you go, wait a minute, I don't get it. How are these new or hard? They're not. It's just the way we write them down. I don't understand John's logic in doing this, but for the third problem, he gives us one of our old style notations back. Just to mess with us? I don't know. I think what he's trying to do is help our brains toggle back and forth between the 2 styles without getting upset at all. And that's fine. So domain equals the reals, that's arrows. We split this out into 2. x minus 2 is greater than 3. That's exactly the same with those flicked off. Then I flick them off, but I reverse this and I change the sign on that. Add 2 to both sides, x is greater than or equal to 5. Add 2 to both sides, x is less than minus 1. Okay, domain is the reals. Look at that again. So greater than 5 and less than minus 1. No equals, so notice I'm leaving the open circles. I'm not coloring those in. Yay! That's the right answer. So look, our brains can go back and forth, and now we're going to do one more of the set builder notation style. Graph, x is an element of the integers such that absolute value of x plus 2 is greater than 4. And then I didn't put those on the beginning, all right? Set builder notation. X is an element of the integers such that absolute value of x plus 2 is greater than 4. All right? So, and I will just say again, John does not explain the absolute value the way we create the two non-absolute value expressions out of an absolute value. He has a very wordy and confusing way of doing that. I don't like his way. So do it my way. X plus 2 is greater than 4. We just get rid of those. And then x plus 2 is less than negative 4. Subtracting 2 from both sides, x is greater than 2. Subtracting 2 from both sides, x is less than minus 6. Right? So now we want to graph these. We want to use the integers. Those are dots. So, oh boy, this is going to have a lot of them. So I'm going to need like negative 8, negative 7, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3. We'll squeeze in one more, 4. This is one that requires a ridiculous number of dots. I could have done with one less. Okay, it needs to be points less than minus 6. So we don't include minus 6 because we're doing dots. So it's minus 7 and minus 8. And then greater than 2 would be 3 and 4. So what I did, as you can see, is I set up my number line so that I would have 2 points on either end that I was actually indicating, so that you would get a sense that, oh yeah, it goes in that way. It's kind of a pain because these numbers were so far apart that we had to do all this in between, but that was my thinking. I wanted to show at least 2 points going in each direction. That's the right answer. Okay, we're done. So that takes care of 2 lessons, 117 and 119. You don't have to do the homework for both. What I want you to do is do the practice of lesson let's do the practice and the problem set for 119. Don't go back and do 117, but you'll have to skip. I'm just looking to see, because we didn't do 118 yet. So skip any problems from 118. 118, because we haven't done that yet. We are going to go back and do 118 tomorrow. So then we'll be evened up again. But for now, we're doing the homework for 119, but we're skipping anything from 118 because we took things out of order. I know, it's complicated, but you figured it out. Thank you, goodbye.